Welcome to section 3.2. We're going to spend 2 days on this section like we did in 3.1. The first day we're going to talk about substitution, which is one method of solving. The second day we're going to talk about elimination. This is something that you did see in Algebra 1, so it should kind of be somewhat familiar, but what I love about this section is the fact that we don't have to graph in order to find where our two lines intersect. And we've noticed as we went through, one, graphing takes a lot of time because you have to solve for the y and then graph it. And two, sometimes the points where they intersect are not nice and it's hard to tell from a graph. So what we're going to do is look at finding the intersection of two lines without actually having to graph. And so algebraically we're going to go through, and I'm going to start through with example 1 first, and you'll notice I'm going to do one and then you're going to do one on your own, okay? And then I'll do a second one and then you'll do one on your own. And you have to do the ones on your own to get the notes points for the day, okay? So let's look at the first one. What I want you to do up here is give yourself a little hint, okay? And this big hint is, in order to use substitution, you want to look for the single variable. And that means basically look for an x or just a y. And if you can find just an x or just a y, then that's what we want to go and solve for. Substitution means whatever you get, you plug it into something else. So it's like a plug and chug idea. So let's look at example 1. I'm going to circle the x because that's the single variable. In order to get x by itself, I need to get rid of the addition of 2y. So to get rid of addition, we subtract 2y. And I end up getting then that x is negative 2y minus 2. And you'll notice that I'm going to put my variable first, just because I'm good with, mx plus b, so I'm going to kind of stay in that, that general look of our equation. Now what we're going to do is we're going to take this negative 2y minus 2 and we're going to plug it into the x in the other equation. So what I get when I do that is 3, and then here's where my x was, plus 4y equals 6. And where the x was, I'm going to put my circled equation in there, negative 2y minus 2. Okay? So I distribute and get negative 6y minus 6 plus 4y equals 6. I'm going to combine like terms first. Negative 6y and a positive 4y is negative 2y. And then I still have a minus 6 equals 6. And now I can start solving a one-step equation from chapter 1 in part A. So I add 6 to both sides. Negative 2y equals 12. When I divide by negative 2, y equals negative 6. And again, the goal of this lesson is to find the point of intersection. So when I talk about that point of intersection like we did in 3.1, this tells me the y value is negative 6. The problem is I don't know what the x value is. But what I can do, since I solved for x in a previous step, I can just plug the y in. So I have x equals negative 2 times negative 6 minus 2. Well, negative 2 times negative 6 is negative 14 minus 2, which is negative 16. So my point of intersection then is negative 16, negative 6. And if we go back to 3.1, we should be able to label our system. And because it intersects at one point, we said this was consistent and independent. And even though we're not graphing, we still feel it's necessary to be able to label this because this talks about the type of graph that you have. And what this means is that these two lines will intersect at this point only once. Okay? Now if I were you, I'd pause the video real quick and try the on your own one right below it. Again, look for your single variable. I'll give you the hint, it's x again. And solve for x, and then go through exactly what we did above. And if you pause it, I'm going to check these answers with you guys tomorrow, but you want to have them done to get your notes points. What I'm going to do though is look at example 2, and I'm going to solve for a different variable this time, because I look at it and I see a single y. And so if I solve for a y, I got to get rid of the negative 2x. So I add 2x to both sides, and I get that y equals 2x, and it was a minus 5, a negative 5, so minus 5. Now this 2x minus 5 is what we plug into the y in my second equation. So I'm going to write my first equation, 6x minus 3. I'm going to put a parentheses where the y was, equals 15. And instead of the y, I'm going to put what I solved, which is 2x minus 5. Okay, now I'm back to chapter 1 again. This negative 3 is going to get distributed. So I have a 6x in front. Negative 3 times 2x is negative 6x. Negative 3 times negative 5 is a positive 15, equals 15. If you notice, 6x minus 6x, these cancel because you have one positive and one negative. So what I'm left with is 15 equals 15. Now this is not an answer we're used to seeing. But if I look at that, is it true? Does 15 equal 15? If you're answering yes, then our answer for number of solutions is infinitely many. Because what that means is that no matter what x is, I can pick any number I want for x. The x's will always cancel out, and I will always get a statement that's true. 15 equals 15. Therefore, there are infinitely many solutions, which means it's one line on top of another. So if I label my system, it's consistent, and because it's infinitely many, it's dependent. Okay? Now, as we go through again, this is 2 examples, and I don't want to take up a ton of your time because we're going to practice a lot in class, and we have a couple of days. But I want to give you the general idea. We look for a single variable and solve for it, and then whatever we've got, we plug into the other equation. You'll come out with a point. You could come out with infinitely many. Our other option was no solution at all, and hopefully you'll see one of those today. But this is the general idea. So that's all I'm going to show for you today in 3.2. The next video will show you an alternative method to solving. So thanks for watching.